Okay, so let's get started with a quick recap of what we have done in the last class. Okay, all right, the quiz is going to be posted on Blackboard. It's going to be an online quiz, and so you'll have the weekend to work on that. Okay, weekend as in, once you start the quiz, you have to stop. It is a timed quiz. That means once you start it, you have, after a set amount of time, you need to finish that. Okay, it's not like you had the whole weekend to finish that quiz. All right. So anyway, the details will be up on the Blackboard. Now let's get back to the class. In the last class, we were discussing. Okay, so these are the things that we covered. We basically covered all the gates, all possible gates that we can find. All right, all the logical building blocks, all kinds of logical building blocks that we'll encounter. Okay, and we also, so that basically, to summarize, we had the fundamental gates that consisted of and, or, not gates. We had, and we know why they're called fundamental gates. We had the universal gates that comprised of your NAND and NOR gates. And then finally, you had the higher order gates that comprised the XOR and XNOR gates. Okay, so your AND, again, these are all operators, and, or, not. These are simple, fundamental, these are the basic logical operators, right? These are all operators. In terms of universal gates, we had the NAND, which is really the inverted version of, or the complemented version of the AND gate, and then you have the NOR. And we have shown that NAND gate and NOR gate, these are universal gates. I can implement each of these fundamental gates with just the NAND gates alone or just the NOR gates alone. Okay, and that's why we are copying. These are the universal gates. And we have also looked at their XOR, the higher order gates, the XOR gates, and XNOR gates. Why are they higher order? Because they can function, because the functionality of these consists of one or more equivalent fundamental gates. Right? For example, for your XOR, A XOR B, I can write this operation as a combination of two fundamental gates, right? Or in fact, more than two fundamental gates, A prime B. So I have one AND gate here, one AND gate here. That's an OR gate. You have NOT operations and so on. So that's the equivalent expression for an XOR gate. Okay, and like again, this is something that I want you to make a note and remember. Okay, every time, because every time you see this expression, you should recognize that corresponds to an XOR operation. Likewise, you have A XNOR B, which I can write this as A prime B prime or AB. Again, something that you should keep that in mind. Okay. Now, so that's good. So we looked at the basic building blocks. Now we are at a stage where we want to put them together. We want to formulate rules whereby we can actually start putting them together to construct more complex logic. Okay. And in the last class, we looked at a very simple example of that, right? And now what I want to do now is to come up with a set of rules by which we can actually do that. Now again, we don't want to come up with any circuit that can perform that logical operation or that conforms to the problem specification. Okay, we want the simplest circuit, a circuit that has the least number of these blocks, because again, remember that each of these gates, the logical building blocks, these are also called active circuits. Now, these are different from passive circuits. If you recall, your passive circuit elements are your resistors, capacitors, inductors. These are the passive circuit elements. On the other hand, these gates are comprised of active elements. Okay, when I say active, that means these have to be powered up. You have to supply power for these elements to work, because these are made up of transistors, which are active circuits. They need to be powered up. Now, when I'm trying to design a circuit, okay, or a computing device, I want to make sure that I want to make sure that what I design is simple. Again, we looked at the list of different things that we want to consider, right? The characteristics when we're trying to go, when we're going about designing a system. Okay, they have to be simple, cost effective, power efficient. Again, the more number of gates you have, the more power it's going to consume, right? So we want to come up with a set of design rules by which we can come up with the simplest circuit that conforms to the problem specification. Okay, all right. Now in the last class, let's take up the example of the last class. Again, we start with the problem statement this time. All right, about the example of a nuclear reactor, right? And we want to come up with a decision circuit that takes in 3 inputs. Okay, so this is what we want to design, a decision circuit that takes in 3 inputs. We call this again A, B, and C. We know what A, B, and C are. A is the input A indicates overheating. Basically, it's a sensor, right? It's the output of a sensor. Now A is true when the temperature sensor indicates overheating. Okay, and this is how we defined A. We had defined B as true if it's a weakened, and we have defined C as true if maintenance is scheduled. And we defined F as the output of this system, the decision circuit. F is true if it's what do we define F? F is true if the power system has to be shut down, right? Or the nuclear reactor is shut down. Yeah, nuclear is the nuclear reactor needs to be shut down. So this is the problem statement. We came up with again. This is some kind of hypothetical situation. It's a simple situation, obviously, when you're trying to come up with a decision circuit for a nuclear reactor, something like a nuclear reactor. It's going to be, it's going to be much more complicated than that. You'll have much more. You will have many more inputs going into the system, and then you're trying to work with all the different combinations of these inputs, coming up with a logic decision, right? So anyway, so let's start with a simple example here. So I have 3 inputs. I know what the inputs are, what the inputs represent, which is given by the problem specification. That's the problem specification. Now I want to come up with the simplest circuit. Okay, how do I do this? Now the first step I would do is to translate this information into a truth table. I want to see the relationship between my inputs and the outputs, and the best way to do that is to compiling that into a truth table. This is what we have done in the last class. So let's do that. Okay, so we have that. So a truth table consists of all possible combinations. We are looking at all possible combinations of the inputs, which we can list here because I have 3 inputs, right? And each input can only take 0 or 1 value, logical value, right? Either it's true or it's false, right? So for 3 inputs, that would basically give me 8 different possible combinations. So I will do that. I have A, B, C. These are my inputs. Okay. I'm going to leave some space here. All right. That's my F. And you'll see why I've left some space there. Again, I will always list out the different combinations in the numerical order. Okay, so 0, 0, 0 corresponds to a numerical value of 0. 0, 0, 1 corresponds to a numerical value of 1. 0, 1, 0 corresponds to a numerical value of 2. 0, 1, 1, that's 3. 1, 0, 0. That's 4. 1, 0, 1 is 5. 1, 1, 0 is 6. 1, 1, 1 is 7. Okay. And my output is true if A is true. If A is true, that means, my system is overheating. Then of course the nuclear reactor has to shut down. So my output is true if A is true, right? So definitely I can just, for these combinations, starting from here, I can list my output to be true. All right. My output is also true, or the system can also shut down when it's a weekend, right? B is true. And when there is no maintenance scheduled. C is true if maintenance is scheduled. C of 0 indicates that there is no maintenance scheduled. So for this particular condition as well, my output is true. So let me like that. And for every other combination, output is false. That means my nuclear reactor has to keep running. So that's the circuit. That's basically a snapshot of the input and output characteristics of the system I want to design. Okay, I want to design a circuit such that when I input, when any of this input happens, I should be getting that corresponding outputs. Okay. All right. Now, in the last class, we also came up with the concept of, or at least we started out describing the concept of minterms, right? Let me call that the minterms. Now, again, going back to the last class, we have defined it in a way. Basically, the minterm would be comprising of three characteristics, right? Three characteristics. The first one is it's a product term. A minterm is a product term. Product term as in it's going to be an AND operation between the inputs. It's a product term between all the inputs. I have three inputs. That means that should be a product term between those three inputs. Okay. The other thing is, or the other characteristics or the attribute of the minterm is, it should be there should be a minterm, a unique minterm for each input combination. Okay, I'm not worried about the outputs at this time. If these are my inputs, for each input combination, I should be having a unique minterm associated with it. Okay. So every time you see this combination, you should immediately say what the corresponding minterm should be. So that's the second attribute. Okay. The third attribute is, now when I plug in these values into that corresponding minterm, every minterm, every input combination should have some corresponding unique minterm. When I plug in the values into that corresponding unique minterm, I should get a unique signature. Okay. So these are the three attributes for the minterms. Now, and in the last class, we guessed one possibility, which is ABC, right? Again, that's a combination of three, that's a product term, A and B and C, that's a product term, okay? It has all the inputs, A, B, and C, right? So the two attributes are satisfied. What about the last one? Is it unique? When I plug in these values into this combination, what am I going to get? This is an AND term, right? A and B and C. 0 and 0 and 0 is 0, right? Okay, that's fine. What about if I plug in these values into this input combination? What would I get? Still 0, right? Because for an AND operation, it's like a product operation, right? Any number times 0 is 0. Very similar to AND operation. And if I have 1 0 in that product term, that brings down the entire expression to 0. Okay? In other words, if you look, so for all of these combinations, because all of these combinations have 1 0 in it, for all of these combinations, this product term is going to give me a 0. So obviously this input combination is definitely not providing me with a unique signature for this input combination. So definitely this particular product term is not a minterm corresponding to this input combination. I hope that makes sense. So what combination can this be a minterm for, or minterm of? Right? So definitely this is not corresponding to this. So what combination would that be? 1, 1, 1. Perfect. Because now let's look at this. If I choose A, B, C to be the minterm, if I say that this is the minterm for this combination, it satisfies all the three attributes, right? This is a product term. This is product term consists of all the three input combinations, all the three inputs. If I plug in these values, 1, 1, 1 into this, I'm going to get a 1. And I'm going to get this 1 only for this combination. So if I plug in any of these other combinations into this product term, that's going to give me a 0. So that this gives me a unique signature only for this input combination. So this particular product term is considered the minterm for this input combination. Okay. All right. Now let's list out for other ones. What about 0, 0, 0? Let's start with 0, 0, 0. What could be a possible minterm for that combination? Again, it has to be a product term between the inputs A prime, B prime, C prime. Perfect. So let's choose A prime, B prime, C prime. And that's the product, that's the minterm for 0, 0, 0. Because if I plug in these values into this expression, A is 0, A prime will become 1, B is 0, B prime is 1, C is 0, C prime is 1, 1 times 1 times 1, that's 1, okay? And that's going to be a 1 only for this input combination. If you plug in any of the other ones, that's going to give me a 0. So that's unique. That has a unique signature only for that input combination. Now let's list out all the combinations, all the minterms, okay? And because these are unique, I can number them. And because I'm always going to follow the sequence, the numerical order for when I'm listing out my input combinations. So I will call this a unique number M0. So A prime, B prime, C prime corresponds to minterm number 0. Okay. What about the second one? What would be the minterm for that? That should be yeah, A prime, B prime, C. That's it. And I will call this M1. And likewise, I'm going to list all of them. A prime, B, C prime, A prime, B, C. So basically, I'm priming every time I see a 0. Okay. This is going to be A, B prime, C prime, A, B prime, C, A, B, C prime. And that's going to correspond to M2, lowercase m, M3, M4, M5, M6, and M7. Okay, so far so good. So why do I need to do this? Again, ultimately, I want to come up with an expression. Right? I should be able to, from the truth table, if I can come up with an expression, like a Boolean expression, because if you recall from the last class, if I have a Boolean expression, that is equivalent to having a circuit built. Expressions and circuits are equivalent. Okay. All right. So those are the minterms. Now I can again write a logical statement. Okay. Using the minterms to my advantage now. Now my f is true. I can say from this truth table, my f is true if this input combination occurs or M2 occurs, right? If this input combination is true, because now I'm going back to my function now. The minterms are basically corresponding to the input combinations. Now I'm trying to write the function in terms of the minterms. Again, I just follow the logical statement now. If it's true, if this input combination occurs in my inputs to the system, or again, or corresponds to a plus operation, remember that, or this input combination occurs at my inputs of the system, or this input combination occurs, or this, right? That's how I wrote my truth table. That's how my truth table is. My f is true if this input combination occurs, or I can say it as M2 occurs, or I can say it as M2, the minterm M2 being true. So if it's true, if this minterm is true, because this minterm is true only for this input combination, or if M4 is true, because M4 is true only for this input combination, or M5 is true, which is true only for this input combination, or M6 is true, or M7 is true. Or in other words, I can write F as M2, or again M2 corresponds to this input combination, this minterm, or M4, or M5, or M6, or M7. Now you can see how I went from a truth table consisting of zeros and ones, and from the truth table I'm trying to get an expression, an algebraic expression. Okay, because once I get an algebraic expression that corresponds to an actual circuit. Or I can write this as, if I want to make this shorter, I can use the symbol sigma, which basically specifies summation operation of the minterms M2, M4, M5. Again, these are the different types of representations, M7. Okay, this is another way of representing the exact same information. I can write this as sigma m, the lowercase m representing the minterms, and followed by the numbers of the position of the minterms. In this case, corresponds to 2, 4, 5, 6, 7. 2, 4, 5, 6, 7. Okay. All right. Now, in terms of the expression, algebraic expression, my expression would read as, let me actually use this space here. So I want to write this as an algebraic expression. My expression would read as F equals, the minterm corresponding to the second position is A prime B C prime, or A B prime C prime, or A B prime C, or A B C prime, or A B C. Okay, you're able to see that. Okay, obviously, so that's, if I implement this expression, again, this expression consists of what do we have here in terms of a circuit. If I want to imagine this as a circuit, what I will have is, how many AND gates do I have? I have 1, 2, because each product term corresponds to an AND operation, right? So I have 1, 2, 3, 4, 5. I have 5 AND gates. These are 3 input AND gates. Okay, 3 inputs, because I have, which within each product term I have 3 variables, right? So these are 3 input AND gates, which are feeding in to a large OR gate. Okay, an OR gate with how many inputs? 1, 2, 1, 2, 3, 4, 5. 5 inputs. So I have 5 AND gates, 5 3-input AND gates. Okay, 5 3-input AND gates that are being fed into a 5-input OR gate. If I want to, these are all 3 inputs. If I were to implement this expression, that's what I would implement it as. Okay. All right. So obviously, if you recall, when we started out with this expression, when we started out with this, we came up with a very simple expression, right? If you recall, it was definitely not as complicated as this. That means we have to do some additional steps to simplify this. So there may be a means by which I should be able to actually simplify this expression in the simpler form. Okay. All right. So that's so obviously that step is still remaining. So that's something that you need to keep in mind. All right. So that's minterms. That's one way of expressing things, one way of obtaining the Boolean expression, which is equivalent to having a circuit. Okay. Now the other way, of course, if I can define something called minterms, which are product terms. Now I would say through symmetry, right? I should also have something called maxterms, which would be sum terms, right? So let's do that now. Let's actually describe maxterms now. So minterms and maxterms are specific to the inputs. Okay. Now for each function, the choice of the minterms or the choice of the maxterms would be unique for each function. But minterms and maxterms themselves are basically specific to the inputs only. All right. So maxterms. Let's define maxterms. The definition would be very identical to the minterms. The only difference is when I say maxterms, these are instead of dealing with product terms, we'll be dealing with sum terms. Okay. Now, again, the attributes are the same. So these are the sum terms. Each input combination will have a unique max term associated with that. Okay. And each unique and these max terms should provide me with a unique signature for that corresponding input combination. Only for the corresponding input combination, not for the other combinations. Now, with that definition, what would be a max term for the first combination 0, 0, 0? Any ideas there? It should be a sum term. That means there should be an OR operations between the inputs, and that should be unique. So each input combination should have a unique max term associated with it, and that max term should provide a unique signature for the corresponding input combination. Any ideas there? What would be a max term for a 0, 0, 0 combination? What could be a possible max term? A plus B plus C. Okay, let's check that out. A plus B plus C. If I plug in these values, I'm going to get a 0, right? 0 or 0 or 0 gives me a 0. 0 or 0 is 0, right? For an OR term, my inputs should have at least 1, 1 for the output to be true, or for the output to be 1, right? For an OR operation. For an OR gate or for an OR operation, my input should have at least 1, 1 for the output to be 0. For output to be 1. Okay. In this case, yes, that gives me 0 as the output. Now, what about if I plug in any of the other values into this max term, into this term? That would give me a 1, right? Because every other combination will have at least 1, 1 in that input combination. So yes, so A plus B plus C is a max term corresponding to this input combination, because that's going to give me a 0, which is unique only for this input combination, not for any other combination. Okay. So that's right. What about the second one? Or what about the 0, 0, 1 combination? What would be a corresponding max term for that? A plus B plus C prime. Perfect. A plus B plus C prime. To be consistent, let me just use the same convention. All right. Right, because A plus B, 0 plus 0 plus C prime, C is 1, C prime is 0, 0 plus 0 plus 0, still 0. And likewise, I can basically list out all the combinations, all the max terms. So this would correspond. So every time I see a 1, I would complement that input variable. So that's A plus B prime plus C. It's going to be A plus B prime plus C prime. A prime plus B plus C. A prime plus B plus C prime. A prime plus B prime plus C. And finally, A prime plus B prime plus C prime. Okay. And when I'm depicting max terms, I would number them with uppercase M. So that will be M0, M1, M2, M3, M4, M5, M6, M7. Okay. Now, can I express my function as max term in the using max terms? How do I do that? Okay. So when I'm trying to express my function as using max terms, I would basically do this, and I will explain to you why that works. Okay. I would basically choose those max terms for which my function is false, which are M0, M1, and M3. Okay. And see why that works in the first place. So what I'm saying is, I can express my function in terms of max terms as f equal to M0 and or product M1 and M3, which is basically, I can also write this as pi. That refers to the product operation M corresponding to max terms, the uppercase M, and then 0, 1, 3. Okay. Which is nothing but A plus B plus C A plus B plus C prime and then A plus B prime plus C prime. How would it work? Would I get the same functionality here? Right? How do I check? Okay, let me see if I can check it through logic, as going through a logical statement. My f is true. What it says is my f is true if this product term is true, and because that's an AND operation, right? This product term is true and this product term is true. Okay, so this has to be true, or this has to be a 1, that has to be a 1, that has to be a 1. So all those three max terms have to be simultaneously 1 for my f to be true. If either one of these is a 0, then that will take my f to be 0. Okay. Well, I would still go by this true. Just hold on for a few minutes, and hopefully that will make things clear. Okay. So f is true, yeah, but when I'm choosing the max terms, I would choose those for which my function is false, and I would write them as a product between the max terms. And why would it work? My f is true if this max term is true, and this max term is true, and this max term is true simultaneously. Now, when are they true? this maxterm is true for every combination. This maxterm is true for every combination other than this, right? You see that my M0 maxterm is true for every combination other than 0, 0, 0 combination. So all of these combinations would work, which would basically give this as true. Okay. Now what about this? So obviously, zero combination, 0, 0, 0 combination is ruled out for this. Okay. Let me do a different color. I hope that makes sense. So except for this combination, let's rule it out. Except for that combination, every other combination will give me a 1 for that maxterm. What about this? A plus B plus C prime. Again, if I look at this truth table, this is going to be a true for every combination other than M1 combination, which is 0, 0, 1 combination. So except for the 0, 0, 1 combination, every other combination would give me this maxterm to be true. And finally, for A plus B prime plus C prime, that's going to give me a 1 for every combination other than 0, 1, 1 combination. Okay. So my F is true if this does not happen, this does not happen, and this does not happen. So what should happen? These combinations. So these are the ones that are remaining. That will give me the true value for all of these combinations. And this is exactly what my function is, right? My function is true for this combination, this combination, this combination, this combination, and this combination. So that's how the maxterm works. Okay, it's not as direct as minterms, but it should make sense. It's logical. It should make logical sense, right? Because here, when we are considering that to be true, you have more than one possibility there. Unlike minterms, where we had only one possibility. So let me take a pause and let me see if you have any questions with that logical explanation. Does that make sense? Just raise your hand if it doesn't make sense. If it doesn't make sense, and let me see if I can explain that again. Any questions on that? Okay. So I hope that makes logical sense. I hope now. So when I'm trying to write, to summarize, when I'm trying to write a function in terms of minterms, I choose my function. I choose those minterms for which my product is true, and write them as sum of products. Right. So when I'm writing in terms of minterms, I would consider that expression f sum of minterms. I would consider that expression as a canonical because it's composed of minterms. It's called canonical sum of products expression. Sum of products expression. When I'm writing this function as a product of max terms, that's a product of max terms. Then that would be corresponding to, that would be called a canonical product of sums, right? This is a product of sums expressions. Okay. Sum of products can also be written as SOP, sum of products, product of sums as POS, product of sums. SOPs and POS. Okay. All right. Now, again, the question remains. Obviously, what I've obtained here looks much more complicated than what we have started out with in the first place. So somehow, there are something missing here. There is some steps, additional steps that are missing that would enable us to simplify the functions. By the way, before we move on to the next part, what would the circuit, if I were to implement this circuit, what would that look like? That would basically look like, I have how many OR gates do I have? I have 1, 2, 3 OR gates, 3 input OR gates, that are feeding into a 3 input AND gate. So if I were to implement that, my implementation would look something like that. Okay. All right. Any questions on this? So far, so good. Okay. So now what we will do, now what we will do is now I need some help from you guys. Make sure that you know these expressions. Note down these expressions because I'm going to erase everything now. Hopefully in your notes you have that expression as well as the minterm expression because I will be using that later. I will be coming back to that later. Okay, so now let's actually start looking at how do we actually go about simplifying these expressions. So for that, I need to basically look at the rules of simplification, okay, and we will examine those rules now. Okay, so I'll examine the Boolean identities first so that I can use those Boolean identities to, to simplify expressions, Boolean expressions. All right, so these are very similar to what you're already familiar with regards to, arithmetic identities. Okay, so let's see these Boolean identities. Let's say let's start with the basics. Let's say I have a Boolean variable x. When I say Boolean variable, what I mean by that is my x can take only 2 values, 0 or 1. Okay, and I'm working with operators here. Okay, so when I do plus, that means it's an that means it's an OR operation. Okay, so x plus 1 or x or 1, what would that correspond to? You're taking some variable x and then you're ORing that to 1. Okay, remember, for an OR gate, if one of the input to the OR gate is a 1, regardless of what the other inputs are, the output is 1, right? So x plus 1 would be a 1. All right, you can plug in the values. If x is 0, 0 plus 1 is 1. If x is 1, 1 plus 1 is 1. Again, that's an OR operation, not an addition operation. X and 1, x and 1 should be x, right? If x is 0, 0 and 1 is 0. If x is 1, 1 and 1 is 1, which is x. What about x and 0? X and 0 is 0, right? What else? X ANDed with its prime, with its complement. What would that be? X and x prime. X and x prime would be always 0, right? Yep. Because if x is 0, x prime is 1. If x is 1, x prime is 0. Either way, you'll have a 0 in the and in the product term, and that will basically make it 0. What about x or x prime? X or x prime is always going to be a 1, right? Because if x is 0, x prime is 1. And if x is 1, x prime is 0. Either way, you'll always have a 1 in the OR expression, That's going to be a 1. Okay. So we will be using these identities to simplify our expressions. Okay. All right. What else? If I have x, if I add another x to that, or when I say add, what I imply is the OR operation. If I have x or x, what should that be? What should that give me? That's x. That's correct. That's x. Because if x is 1, 1 or 1 is 1. X is 0, 0 or 0 is 0. Right? And I can generalize that. In other words, I can say if I OR a variable to itself any number of times, it's still x. I can also use that in simplification, as you will see later on. Likewise, I can say x and x and x any number of times would still produce x. Okay. All right. Then you have the familiar ones. Yeah, x or y, the operator follows the commutative relationship. So x or y is the same as y or x. X, similarly, x or y plus z, it also follows the associative relationship. It can be written as x plus y. Okay, x or y plus z. Okay, same thing. So these are something that you're already familiar with. Let's say you also have the distributive law, x and y or z, so you can distribute your product. Okay, that's a good idea. X or 0 is x, right? X or 0 is x, because if x doesn't matter if what x is. I mean, this is because this is 0. It's almost like adding 0 to the number would give you the same number, right? Yeah. Thank you for reminding me that. X and y or z, I can distribute just like how you can distribute in arithmetic. This product operation, I can distribute this. I can write this as x or y, x and y, or x and z. Okay. Now we have an additional distributive law. Just like how I can distribute product operation, I can also distribute the sum operator or the OR operation, which is not there in the arithmetic operations. In other words, what I'm saying is, if I have an expression like this, x plus yz, all right, I can write this. I can distribute my OR operator to write this as x or y and x or z. So that's permitted here. That works here. Okay. Let's see. What else do we have? Yeah. Those are done. Okay. We also have this. If I take a variable x, prime it again, that gives me back my x. Okay. All right. So that's good. That's well and good. Now we also have an important identity called the De Morgan's theorem. Okay. Something to remember. What it states is that x plus y whole prime is really not equal to x prime plus y prime. We've already seen that. It's not equal to x prime plus y prime. What it's equal to is, if I have an expression like this, where my entire expression is complemented, x plus y whole prime, the complement is over the entire expression, I can write this as, I would basically write down the individual variables, complement the individual variables, x prime becomes x prime, y becomes y prime, and complement the operator between them. Here I have plus operation. If I complement this, that's going to be transformed into a product operation. So x plus y whole prime becomes x prime and y prime. Complement the individual variables as well as the operation between them. Okay? And it works other ways too. So for example, if I have xy whole prime, okay, same thing. I complement the individual variables x prime and y prime, and then the operator between them is a product operation. I complement that as well. In this case, that will become plus. So that's the De Morgan's theorem. And as a matter of fact, we have used this in the last class when we were trying to implement the OR operation using NAND gates alone. Remember how we did that? Using NAND gates alone, the OR operation was something like this, right? We complemented the inputs. Let me call that A, we call that B, then we call that F. In this case, my F is what? A prime. Again, that's A prime times B prime whole prime, right? That's a NAND gate. I'm applying A prime and B prime to this NAND operation, and that's the output of the NAND gate. Now I can apply my De Morgan's theorem here. What do I get if I apply the De Morgan's theorem? My F becomes, I complement the individual variables. I have A prime here, A prime prime will be A, B prime prime will be B. I complement the operator between them, which is product there, that becomes plus. And that's how we got F equals A plus B in the last class. Okay, I have shown that using the De Morgan's theorem here. I hope that makes sense. So that's A prime dot B prime whole prime. Every time I see the whole prime, the prime over the entire expression, with whether it's a product expression or a sum expression, I can apply the De Morgan's theorem to break it down, okay, to take out the whole prime and complement the individual variables. That's how I did this here. So A prime prime becomes A, B prime prime became B, the product became a plus operator. That's how we got the OR operation from the NAND gates alone in the last class. Okay, that's good. All right, so now let's actually start using these and look at some of the, and try to simplify some expressions. So let's say I have an expression x plus x prime y, a simple expression x plus x prime y. X plus x prime y. And I would like to simplify that. Well, how do I do this? Now in this case, can I distribute my plus operation to write this as, or in other words, I'm trying to use this identity here, apply this identity, I have x plus x prime, x plus y, right? X plus x prime y would be x plus x prime, x plus y. X plus x prime would be what? This goes to, it's always going to be a 1, right? Because if x is 1, x prime is 0. If x is 0, x prime is 1. Either way, that's going to be a 1 times x plus y, which is x plus y. Okay. All right. What else? Let's see another one. Another example. X prime, y prime, z prime. Oh, no z. There is no z prime here. X prime, y prime, z plus x prime, y, z plus x, y prime. And I would like to simplify that using Boolean identities. Okay. Now, how do I do this? What kind of identity can I use here? Now, what I would do is always when I have something like this, x prime, y prime, z, x prime, y, z. Okay. When I have something like this, I will always use this identity. When I have two product terms, a, b, c, and let's say a, b, c prime. All right. I have two product terms, and I only have one variable that changes between those product terms. Okay. In this case, between these two product terms, this is the variable, right? That is changing from c to c prime. Two product terms, one variable that can be changed, only one variable that is changing. That means I can basically take the unchanged variables. In this case, my a and b are the unchanged variables. I can take these as a common factor, right? And that will, I can write this as c plus c prime. Just like what you would do in arithmetic algebra, right? You would do the same thing, like AB. I take the AB as a common factor, C plus C prime. Now you know what C plus C prime is. C plus C prime will be 1. So that gives me AB. So I can use this trick for the simplification. Most of the time you'll be using that trick. I'll be looking at expressions, product expressions. I'll be combining them every time I see common factors and one variable that's changing. Okay. Now I can also see the same thing here, as you can see here. Between these two expressions, between these two product terms, I can see that only one variable changes. My z is common, my x prime is common, only y changes from y to y prime. So I can take my x prime z as a common factor here. That will become y prime plus y. And then I have x y prime. Again, that goes to 1. So I end up with x prime z plus xy prime. I don't think we'll be able to simplify it any further. But yeah, there you go. Because I don't see any other common factors there that I can actually factor. So that's it. Okay. So basically, you're trying to use the Boolean identities to simplify your expressions, to eliminate variables and obtain a simplified expression. Because every time I eliminate a variable, I'm simplifying my circuit, because that's the consequence of eliminating variables or eliminating terms. Okay. Now what I'm going to do now is let's get back to the expression, the minterm expression, the canonical sum of products expression, and try to apply some of these identities to simplify this expression. Going back to the example, our sum of products expression, the canonical sum of product expression was, my f was what? Let's see, a prime b c prime, a prime b c prime, or a b prime c prime, a b prime c, ABC prime plus ABC. That's ABC prime plus ABC. Okay? So this is the canonical sum of products expression we got directly from the truth table. If you recall, if you just go back to your notes, this is what we got. And we would like to simplify this using the Boolean identities now. Okay. Again, the trick is you would combine these product terms, okay, taking a common factor. I will combine those product terms where going from one product term to the next, I only have one variable change that's happening. Okay. Let's see how we can combine them. Can I combine these two? I have a prime. Okay, that's changing. B prime. So I have two variables that are changing here. So let's not combine them. What about these two? I have a common, b prime common. I can combine them. So the only variable that changes is c, going from c prime to c. So I can combine these two. That's good. What about these two? Can I combine these? I have ab as a common factor. I can already see. I can combine these two as well. Right. So what do I get? So I get a prime b c prime, or I take my ab prime as a common factor, then that will combine c prime plus c, or again I take ab as a common factor, c prime plus c. Okay. Now c prime plus c, again using the identity, any variable odd with its complement is always going to be a 1, so that goes to 1. This goes to 1 as well. So my expression basically becomes a prime bc prime plus ab prime plus ab. Now I can see that these two terms also can be combined. Within these two terms, I have a as a common factor, b changes. So I can basically factor out a. I can write this as a prime bc prime plus a times b prime plus b. Again, that goes to 1. So I might as well just take that out. I'm ending up with a plus a prime bc prime. Can I further simplify this? Or is that it? Can I further simplify it using any other identity? Okay. Well, let me use this identity. Okay. If I have x plus x plus x, any number of x's, if I add another x to that, my expression does not change. It's still going to be x, right? If I add another x here, that's not going to change the expression. It's still going to be an x. Okay. So in this case, I see that my a prime bc prime, which we carried out, which we did not combine with anything, this could actually be combined with, let's say, a prime b. Let's see, what can we combine this with? A prime. Yeah, I could have combined this in my first step, even though I did not do it. I could have combined this one with this one, right? Do you see that? But then I used up this one. I used up here. But then, I could have always done this. I could have always added another one of that, a, b, c prime here, and that would not have changed the expression itself, right? Does it change the expression? Just by adding another one, the exact same term, a, b, c prime, that would not have changed the expression by this identity, right? In other words, if I add this here, a, b, c prime, the expression itself is not changed by this identity. But now that allows me to combine these two. Let's see what do we get. So now I have a plus, again here b, c prime are common factors. I can take that out, and then I have a prime plus a, and that goes to 1. So I end up with a plus bc prime. So I use the Boolean identities to simplify my expression. Okay. Does that make sense? Any questions on this? Again, this is not a very intuitive idea. I understand that it may, this idea may slip from our mind. Okay, because it's not really easy to remember all the identities all the time. You can remember these ones, the simple ones, but this is something that's that may slip your mind. Another way of looking at that, okay, that's one way. I added that variable again without changing the value of the function. I can do that because by this identity. Let's see if we can do an alternative way. Again, what I ended up here was with this expression, right? A prime bc prime, a prime bc prime plus a. Okay. Now I can again use the distributive law. I can distribute my plus operation, right? So I can write this as a plus a prime and a plus bc prime. Again, what I'm using here is if I have x plus yz, I can write this as x plus y and x plus z. That's the same identity I've used here. Again, I'm just trying to show different ways that we can simplify. Again, a plus a prime goes to 1. In this case, I again end up with a plus bc prime. Without using this identity, this time I've used this identity, I can get the same answer. Okay, so that's good. Now, the problem with this approach, as you can already see, is we don't know where to stop. This is again a comparatively simple example that we have taken. But for a more complex example that contains more inputs, more number of terms, it's not very easy to see where to stop. We may think that after simplification, we may think that this is the simplest form, but maybe we have overlooked an identity there. Maybe if I had used that identity, that could have been more further simplified. So there are some issues associated with this way of doing things, with this way of using Boolean identities to simplify my expressions, to obtain my simplest function. Okay. All right. Can I further simplify this? Again, that's the question, right? Do we know if we can use any other identity to simplify this further? Maybe not. Okay, so most likely this is the simplest form. And if you recall, that's exactly what we started out with in the first place, in the last class. Okay. All right. Now what we will do is we will do the same thing for the using Boolean identities. We'll do the same process of simplification for the max terms expression, okay, and see if we can get the same thing. You also do, okay, this one, okay, a prime bc prime. Now again, okay, so the question was, okay, I have this expression a plus a prime bc prime. Can I use a De Morgan's theorem in any way to simplify this? Oftentimes we don't use De Morgan's theorem to simplify expressions. That's more, well, I would take that back. How do I use a De Morgan's theorem here? Typically, when I would use a De Morgan's theorem when I have an expression that has the complement operation over the entire product term. Here I don't have that, so I don't think that's possible to use De Morgan's theorem here. If it was something like this, then I would use the De Morgan's theorem to break it down into the individual components so that I may be able to combine with the other terms here. But here I don't have that, so most likely I would not be needing De Morgan's theorem here. But that's a good point, good observation. Does it make sense? Okay, great. All right, so let's start with the max terms, the canonical product of sums expression, and then let's try to simplify that now using the Boolean identities again. So the next homework will be on this, on the simplification of these. Okay. Now, what was the, yeah. So what I had was f equals a plus b plus c times a plus b plus c prime times a plus b prime plus c prime. Just a side note. Now, remember that we had minterm for 0, 0, 0 combination of ABC. The minterm corresponding to that was a prime, b prime, c prime. And the max term corresponding to that was a plus b plus c. Okay. Now, if you notice, if I have a prime, b prime, c prime, if I take the complement of that, okay, what would I get? If you take any minterm, complement that, I would get the corresponding max term. Okay, so in this case, I would get a, again, that's the complement of the entire product term. So individual variables are complemented. So in this case, a prime prime will be a, b prime prime will be b, c prime primes will be c. The operators are also complemented, so that will be plus. So the complement of the minterm gives you the max term. Okay. All right. Just a side note. All right. So we are almost out of time. However, what kind of what would I use here? Again, in this case, I would use this. I would use this identity. The fact that x times x prime is 0, right? X added with x with the complement of itself is always 0, and I'll also use this x plus y times x plus z is x plus yc. In other words, if I have an expression like this, okay, a product of two OR terms, I have a common variable like this, I can take out the common variable and add the rest of these variables here. So in this case, between this expression and this expression, I have one variable that changes, the rest of the variables are basically not changing, right? So I can write this as a plus b plus c times c prime times a plus b prime plus c prime. Again, same combination. I go from one expression to the next expression, look for the common terms, take them out, and then the uncommon terms will be basically going like this. The reason why I write that is because c times c prime goes to 0. So because that makes it a plus b times plus b prime plus c prime. Okay. Now I will leave this to you guys as an exercise to see how we can simplify this further using the Boolean identities, using the list of Boolean identities. I'd like to see if you can simplify this further and get me the same expression that we started out with, that we got for the minterm simplification. Okay. All right. So with that, yeah.
I have a quick question real quick.
Yes.
Isn't this the demorgs? Are we doing the demorgs for the minterms since we're doing the complements of?
Come again? De Morgan's of minterms? Can you repeat that question? Is De Morgan the same as taking the complement? Okay. You take the complement and apply the De Morgan's theorem. Okay. You take if I were to take the complement of an expression, I would apply the De Morgan's theorem to write this as a prime and b prime to separate these out. Take out the but De Morgan's theorem, it's you're taking the De Morgan's it doesn't go the other way around. You take the complement, apply the De Morgan's theorem to get this. I hope that makes sense.
Yeah, it does. I just cut off the middle, but it's okay. I think I got it.
Okay, great. All right. Any other questions before we end this class? Okay, so if you don't have any other questions, then let's conclude here.